Okay, we have to find the direction of the magnetic force felt by each of the four sides of the loop. So if you recall, the magnetic force is Li cross B, where this is the current of the loop and this is the external magnetic field that the loop is immersed in. We use the palm, thumb, finger rule. And of course the magnitude of the force is Lib sine theta. Okay, so let's consider the left-hand side of the loop. On the left-hand side of the loop, theta, the angle between the current, which goes down, and the magnetic field that goes up is 180 degrees, and so the magnetic field there is 0, right, because the sine theta term is 0. Over on the right-hand side, we have a similar problem. The current goes up, and the magnetic field goes up. They're parallel to one another, so theta is equal to 0 degrees. And so again, the magnetic field is equal to 0. Okay? So 0 here, and 0 over here. Now for the top and the bottom, well, for the top, let's see, the current is going to the left, and so if we point our thumb to the left and our fingers in the direction of the external field, then that results in a downward magnetic force that goes into the page. Well, not down, it's into the page. And over here, if we have a current that points to the right and a magnetic field that points up, that results in a magnetic field, or a magnetic force that points out of the page. Okay, so that's part A. Part B, we need to find the magnitude of the torque acting on the loop. Well, our formula for that is mu cross B, where mu is NIA, and then B is that external field times sine theta. Now theta here is the angle between the magnetic field of the loop and the external magnetic field. Well, the magnetic field of the loop, if you look inside the loop, the right-hand rule tells us that the magnetic field, due to all these wires inside the loop, points out of the page. Okay, so that means the angle theta between, now this is a single turn, so n is 1. This angle theta is going to be 90 degrees. Okay, now the area in this case will do 0.24 multiplied by 0.12, and then the external field is 3.5. Okay, sine 90. So I just got to multiply all that stuff together, and I get 0.022 Newton meters for the torque. Okay, and I just need the magnitude of the torque. All right, and then for part C, in what direction does the loop's magnetic field point in the center of the loop? Well, we kind of did that already. Right, for any of these given wires, you can curl your fingers around it and see that the magnetic field outside of the loop points into the page, and the magnetic field inside the loop points out of the page, and that is due to right-hand rule number 1, the curl rule. Okay, and then for part D, in order for the torque to be minimized, in what direction must the loop's magnetic field point? Well, torque is minimized when theta is equal to 0 or 180. And so we want the loop to point in the same direction as the external field. We want it to point up. So B loop must point up in the same direction as the external field in order to minimize the torque.